So we've talked about Boyle's law individually, and we recognize that if the temperature and the amount of gas is constant, the pressure and the volume are inversely related. That is, P times V would be a constant. And for Charles, if the amount of gas was constant and the pressure was held constant, we saw that volume and Kelvin temperature were directly related. So volume over temperature was a constant. But what if we had a situation where we only held the amount of gas inside constant, and we started to squeeze our balloon, and at the same time we started to put a little heat under it? Then what? What would happen? Find that we would have these three variables working together in the same direction, so that pressure and volume over temperature would equal a constant if the amount of gas is held constant. This is what is known as the combined gas law, and that is what we are going to talk about today. So the combined gas law, we're going to see that we need to, again, focus and make sure that when we are using temperature, it has to be in Kelvin units. The only other thing we're going to watch out for is whatever unit P1 is in, same for P2. Whatever unit V1 is in, V2 would also have to be that unit. And our hint that we're going to be using the combined gas law is that they will talk about the amount of gas being constant, but we're going to have two different sets of conditions. Pressure, volume, and temperature will be changing in relation to each other. So when we read this example problem here, we see that we're given an oxygen gas with a volume, pressure, and temperature. They're asking for the new volume if the pressure changes and the temperature changes. So we have two different completely sets of conditions, which means this is when we would want to use the combined gas law. So we know that P1V1 over T1 is going to equal P2V2 over T2. Remembering that we must put our temperature in Kelvin and make sure that our pressure units agree on both sides. Doesn't matter whether we keep them in kPa or atmosphere, so long as we keep them the same for both sides. So let's plug in our values for first set of conditions. So P1 is going to be 71.8 kPa, and V1 is 7.84 centimeters cubed. And a reminder, we need T1 in Kelvin, so we're going to have 25 plus 273, and that's going to give us 298 Kelvin. And we're going to set that equal to our values for second set of conditions. We see immediately that our pressure is in atmosphere. So we're going to need to convert 1.30 atmospheres to kPa, because that was what was used on the other side. So we have 1 atmosphere is 101.3 kPa, and if I plug that in our calculator, I am going to get 132 kPa. So now we can plug in a pressure of 132 kPa. We're being asked to find the new volume, and again, temperature must be in Kelvin, so we're going to add 273 to that. Now we'll cross multiply to solve. And now if we simplify and isolate V2, we find that V2 would equal 3.91 centimeters cubed. Did we answer the question? Well, we got our volume, but they wanted in decimeters cubed. So our final conversion, 3.91 centimeters cubed. And a reminder, there are 1,000 centimeters cubed in a decimeter cubed. So we're really just moving our decimal 3 places to the left, and we get 0.00391 decimeters cubed. That's our final answer. The second gas law that we're going to continue with here today is simply known as Avogadro's law. So Avogadro's law, we are actually going to start talking about the quantities. So in this case, when temperature and pressure are held constant, so you're just blowing up a balloon. Remember, a balloon, the volume isn't rigid, so that could change. And I could be adding more and more air into it, so the amount of gas that is present would be changing. So they're directly related. In lay terms, that means if I put more gas in, the volume increase, and opposite, if volume goes down, the amount of moles must have gone down. So our equation is V1 over N1 equals V2 over N2, where V is volume and is the amount of gas in terms of moles. Our hints that we would want to use this law would be that in the problem they tell us temperature and pressure are constant. So in our final problem, as we read through, we have 4.8 liters of helium gas, and there's 0.22 moles in that. And they want to know how many more moles of helium had to be added to the sample to obtain a volume of 6.4 liters. Assume temperature and pressure are constant. So we know that we are using Avogadro's law. So V1 over N1 is going to equal V2 over N2. Okay, so for V1 we have 4.8 liters, and N1 we have 0.22 moles of helium. We're being asked what is our new amount in terms of moles, so we're looking for N2 if the volume is now 6.4 liters. Okay, so we're going to want to cross multiply to solve, giving us our liters cancel. We have to make sure they're in the same units. So we have 4.8 times N2 will equal 0.22 moles times 6.4. And when we reduce that, we're going to find that N2 equals 0.29 moles. Now notice that was not the question. They asked how many additional moles need to be added to that volume. So we need to subtract those two numbers. So 0.29 minus 0.22, and we would have 0.07 additional helium moles need to be added. That would be our final answer. Just a quick comment when we are using our combined gas law, for you to see that they are very closely related to Charles and Boyle's law, and that it isn't a whole lot of equations we have to memorize. So remember, if we always start with the combined gas law here, Boyle's law tells us temperature is constant. So that would mean T1 equals T2. They would cancel, and I would be left with Boyle's law, P1V1 equals P2V2. Similarly, if we had Charles' law, where we're looking at the relation between volume and temperature, that would mean pressure is constant. So P1 would equal P2, and they would cancel. Notice what remains is Charles' law. V1 over T1 equals V2 over T2. And finally, we can look at Gay-Lussac's law, where we are saying that the volume is constant. So like in an aerosol container, volume 1 equals volume 2 if we have a rigid container. And that would leave us with Gay-Lussac's law, P1 over T1 equals P2 over V2. So I want you to recognize that knowing the combined gas law allows you to know Charles' law and Boyle's law very easily. So it isn't as much remembering as you might think. And then we threw in good old Avogadro's law here today. And we're going to see how all of that is going to be helpful as we look at the ideal gas law tomorrow. Okay, thanks.